Alright, so let me go and just show it to you. So if you remember, it should be in your documents. You had a folder called Python Neuro 2018. If you cloned it last time, remember if it's LS for Mac and it's dir for Windows to be able to see the listing in your terminal/command prompt. So if you go into that folder, now you should be able to do git pull upstream master. Oops, master. So remember, upstream is something we registered last time. It's basically an alias to the upstream in terms of GitHub. So that's basically where you forked from. So that actually points to the Edgar's Guide / Python Neuro 2018. So I've updated some stuff last night. So if you run this now, it should get the latest content from there. If you made any changes in between, there's a non-zero probability it's going to pop up a Vim window to suggest that there's a merge that has to occur. And it should happen. So if you're Windows and if you follow the instruction to set the VS Code here's your thing, it will pop up a VS Code and it will say something like merge commit or something like that. In that case, all you have to do is just save and then quit. And that's just a way to say, okay, I'm fine with this merge. This is a good message to go along with it. Only problem is like if you're actually doing this on the Mac side, and if you unless you've gone through like some instruction which I haven't given you on how to set up the VS Code as the editor, it starts Vim, and unless you know Vim, it gives you it's a pretty fairly weird interface to work with, right? So in that case, all you have to do is hit escape a couple times to make sure that you're outside of the insert mode, and then type :WQ for write and quit. And that will actually save it and get you out of the Vim. Okay, I'll have probably a video segment showing this because when you work in terminal, Vim could be as if it's a curse, right? So unless you know Vim, then once in a while this text editor shows up in O in terminal, and it really doesn't work the way you expect, right? Like you actually use keys like J, H, and K and L to move around up and down and left and right, and it also has this idea of command mode versus insert mode, and if you get stuck in one and you feel like you don't know how to get out of it. So hopefully, because you've touched Jupyter Lab, there was also this concept of command mode and insert mode, or command mode and edit mode, right? It was actually inspired by something like Vim. So there's the idea of like getting in and you're now editing something like in the cell, or you're outside and now some keystrokes could actually mean commands. And same exact concept applies to Vim, except that now you need to know the keystrokes, right? So the two friendliest or two most useful commands to learn for Vim, and I have part of it listed out in this PDF. I'll add the other one is the how to quit, right? Because most of the time you actually just want to quit out of it. So you hit escape many times to make sure you're in the command mode, and you do :Q. That usually lets you quit if you do :Q and enter. That usually lets you quit. If it still doesn't let you do it because maybe you accidentally modified a file and they will say, oh, there's some unsafe changes, you must do something about it first. If you just say :Q with exclamation mark, that forcibly quits. So that's a very good one to know, like just in general. If you're not going to be familiar with the Vim, that's a good one to know. And alternatively, if you actually want to accept what's being suggested and just write it out and save it and quit, then you say :WQ to write and quit. This is something you have to do for merge. Again, I'll have these descriptions added to the PDF later. But if you encounter it, that's what it is, so you don't have to freak out. It's not the friendliest one, but it will be a good editor to learn. It's just not something I would necessarily recommend per se. Nowadays, there's so many good editors like VS Code that the need to learn something like Vim has decreased quite a bit. Okay, so I know the couple aren't going to be able to make it today anyway. There's many actually told me, so I'll probably just go ahead and get started. So hopefully this procedure of pulling from upstream work, it should suggest something along the line of there's a new notebook like 04 plotting with matplotlib. So with all of that confirmed, still inside the terminal, what you want to do is just go ahead and launch the Jupyter Lab like last time. And usually just opens up where you left off. If you still have a running version from last time, like there's actually a good chance that that's the case unless you explicitly quit out of it, then you should be able to go to the browser and just type in localhost :8888, and it should take you to the running instance of the Jupyter Notebook. If you close out the terminal window, then it did shut down the server, so you just have to run the Jupyter Lab again. All right, so we'll continue off where we left last time. Let's go on. So last time we were talking about the NumPy arrays and how to create ones, and there are a couple functions associated with creation. Let me actually put this little. And we talk about how you can index and slice an array just like you can do for lists. This allows you to manipulate it. We talk about also reshaping it to start with the flat array and turn it into shape of desired shape. And we also talk about the fact you can modify an array. You can index into a single element and change one element at a time, or you can index at the row or even a column, or even a particular subset and modify all of them at once. So that's something that goes beyond just a simple list. And then we also talked about copies and views and how that if you were to do a slice to extract, say, a row, it's a view, in that if you modify it, it also modifies the original array from which you got the row from or column from. Okay. So this view concept will come back once in a while. We're going to basically look at a couple functions that returns what looks like a new array, but you have to be aware whether it's going to be a copy of an array or it's going to be a view of an array, because that determines whether modifying that is going to also affect what it came from. Okay, so that's all I know, basically just handling array, but we haven't really done the most important thing with array, which is working with them to do computation. After all, this is what arrays are for. So let's start with something pretty simple. So if you were to define, if you're just starting Notebook, by the way, you do probably want to run towards the very beginning, the importing of the NumPy. So at least minimally make sure you have imported NumPy. You could have just done and create a cell and do it there. So let me go back. There. So you could have actually just created a cell here and just imported. Oops. Just to make sure you have the packages around. So remember that arange lets you create a sequence of numbers just like range for list creation or the iterable creation. So here I'm just creating range going from 0 to 4. So up to 5, specifying up to 5, but not including 5, right? So if you were to do a single operation like adding 3 to a NumPy array, what it ends up doing is what you probably expect out of, like, say, adding a scalar value like 3 onto a vector when it comes to math, right? It will basically add that number to every element. If you were to do something like exponentiation, so if you x square, where x is an array, well, what this actually end up doing is going to be performing at what's known as element-wise operation. Basically, it just visits each and every element and then square each of them. So here, since it's 0 through 4, we expect it now to go 0 to 16. Okay, so here I'm just doing slightly differently. So I'm now creating a vector or array entirely filled with ones. So remember, the ones gives you array filled with ones of specified size. So here's going to be a flat array with 5 elements in it. So it's going to be all filled with ones, and if I add 5 to all of them, well, I expect it to be filled with entirely 6. Now things become a bit more interesting when you operate with 2 arrays simultaneously. So here we're taking x, so remember x is 0 to 4, and y, which is now filled with 6's. If you were to subtract one from the other, given that they are matching in size, they both have 5 elements in it, it performs an element-wise subtraction. So here it's a bit harder to see because on one side everything is 6, but here what it ended up doing is just it went to pairs of matching position and performed the subtraction. So this is element-wise subtraction. And this is no different than what you'd expect if you were to say subtract 2 vectors. And just to show, you can also work on a couple built-in functions to work with NumPy array. So a couple sessions back we talked about a package called or module called math, from which you can import special functions like square roots, sines, and cosines. Those are well behaved, but promise they're not aware of NumPy. They were not built for NumPy. So if you were to try to just work on, like, apply that on NumPy array, it has a bit of like kinks that does not going to perfectly work. So NumPy comes with their own version, behaves the same way, except that it understands NumPy array. So if you were to do np square root, so this is a square root defined under NumPy package, and if you pass in an array, it applies that function on every element one at a time. So that's again an element-wise operation. Here I'm just taking the square root of 0 up to 4. Okay, things become actually more interesting and perhaps start to get out of like what you might expect based on this idea of maybe arrays representing vectors and matrices when you say multiply two matrices together. So in NumPy array, when you try to represent a matrix, well, that's essentially just trying to represent a two-dimensional array. So remember, the creation strategy was something like you give a list of lists, and it defines the last dimension first. In this case, it defines columns and then rows of columns. So this, let me actually just look at it. So if I were to define like this, A looks like that, and B looks like this. Okay. Now, any idea what will happen if I multiply A times B? So B, if you're coming from matrix algebra, B is an identity matrix. So since these are matching in size, and if you're thinking in terms of matrices, you might expect, well, A multiplied by B, where B's identity matrix should just give me back A. That's what you would expect if you expect this to be performing a matrix multiplication. However, if you actually multiply the two, you get something like this. So any guess what happened? So it's actually performing element-wise multiplication. It just finds the corresponding location, multiply them up, and that becomes the result in the resulting array. So the default for NumPy array is to always perform matching element-wise operation. If you want a fancy name to go along with operation like this, where it's element by element multiplication, this is sometimes known as a Hadamard product. But more often just referred to as element-wise multiplication. Now, obviously, if you really think on these matrices, you actually do want to once in a while perform an actual matrix multiplication. There are functions for that, but there is also a nice convenient notation for this, and this is an at symbol. Yeah, they really didn't have anything else to use, so they just kind of went with the at symbol. So if you do x at b, this is read as a matrix multiplication. And here, because B is now really acting as an identity matrix, if you multiply A with B, it just returns the A unmodified, just like what you expect out of an identity matrix multiplication. Okay, so one thing about NumPy array is not only it's able to represent vectors and matrices in higher order structures like tensors in more convenient fashion than lists, but it's also implemented in such a way that it actually operates, like computes these things in much faster manner compared to what you could do with list. So rather than just telling you that, I can actually demonstrate that to you. So here, what I've done is I take range of 100, which gives you from 0 all the way to 100, but not including 100, so 0 all the way to 99. I remember range returns a range object. It's an iterable object. But here I actually want it as a list. So I went ahead and convert it into a list. And if you print it out, obviously, it's like a long list all the way going up all the way to 100. So I can actually unfold it. Now, in order to see how fast you can do computations with it, there's a nice utility that comes with the Jupyter Notebook, which are these like things that starts with %, or %. These are called either inline magic or cell magic, depending on what type you're talking about. And without going too much into detail, you can probably guess that if I were to put %, time it, it's going to do something about timing what you're about to perform. So here, if I actually start a cell with %, time it and run the cell, it actually runs the content of the cell actually many times, and then gives you on average how long does it take to compute that one cell. So this is something you will use to evaluate the efficiency of what you wrote. So here what I'm doing is I want to actually compute the square of each element. So I want to do element-wise square. And one way to do that is for me to create a new list, and I iterate through the original list, that's 0 to 99, and then append the squared version of element at a time. So you can go ahead and run it. It will take a bit of time because remember it's running this many times, so you can give your own average how long it takes to compute this. And here it came back saying it takes on average about 26.1 microsecond to compute this one cell. Okay, 26.1 is actually not too bad. That sounds fast enough, right? If you were to just run this, obviously it feels fairly instantaneous. Now, okay, here's one aside I gave that, and this I actually have an extra notebook for. We're going to touch upon later. But there's actually a way to express an expression like this where you're creating a new list by visiting elements from an existing list and just slightly modifying it. You can actually take something like this. Because this is such a common pattern, there's a shortcut for doing it in Python called list comprehension. I'm not touching on it because I actually have an extra notebook that if you're curious, you can go and look at it and learn at your own time. That's actually this extra one list comprehension notebook. So it's actually going to be part of your homework assignment. More like a bonus on your homework assignment. If you're curious, read up on it. I give you a fairly thorough description of how this works. But you can basically imagine that this does exactly the same computation as here. It's just that it's much simpler. And because it doesn't have that extra step of creating an empty list and then putting it in, it tends to be slightly faster. So here it's really just slightly faster. It's 22.7 microseconds instead of 26.1 microsecond. So that's not a huge time bonus, it's just shorter in terms of lines of code. But real benefit comes, of course, when you work with NumPy array. So here I create a NumPy array that goes from 0 to 99, and now I'm timing the operation. So also note the fact that notation is much simpler. All I have to do is take an array and raise the entire thing to the second power, and it will do element-wise squaring. If I run it, it's taking time to compute how long it takes. You can see it's 557 nanoseconds. So this is approximately a factor of 40 times faster compared to what you can do with list. So a factor of 40, I mean, both of them are in microsecond, nanosecond regime. It feels exceedingly fast. But this factor of 40 matters a lot. Just imagine something that actually could have taken a month if you're just doing everything with the list could be potentially done in a day. And hence, these factors matter a lot to the point that you probably always want to be working with NumPy array if you're doing numerical computation. So this is one reason, if anything, to be using NumPy array to do your numerical computations. Okay, so there are more operations you can perform on it. So if I were to create two arrays again, so A and B, just to show the content, so nothing too fancy about it. So here, one is just sequential 1, 2, 3, 4. Other one has a bit more I pick 4s and 2s and puts in random location. You can check for element-wise equality. So if you say A equals B, it compares one element at a time at the matching location and gives you back an array of trues and falses. So this is something I haven't talked about, is that so far we've been dealing with an array that only contains numbers. It could be integers or floats, but it's been so far only numerical arrays we've been working with. But just like lists can contain anything inside, arrays can actually also contain other value types such as booleans or even strings. The only difference being that array actually expects you, the entire array, to be of same type to be efficient about it. So you can have a mixed type, but that actually decreases the efficiency of an array. So for a vast majority of the time, you'll have an array that contains only one data type. So here, if you were to do a comparison, it returns an array of booleans. And you can, of course, do A compare against the tree, and there should be only one true inside because only one of them has a value 3. You can also do inequality in terms of comparison, greater than, so A greater than B, A is less than 4, and all the other ones you're already familiar with. A less than or equal to, greater than or equal to, all of these are something you can work with. Now, to continue along, and I already kind of showed the example of NP square root, these functions that's provided with NumPy to work on one element at a time, these element-wise functions, they actually have a name called universal functions. So when, like in terms of NumPy lingo, these are known as universal functions or ufuncs for short. And it's just a way to refer to these classes of function that comes with NumPy array. So here I just create an array that goes from 0 to 9. And we already saw square root. There's obviously sine, where it expects this to be in radians. And there's also log. This actually is by default, it's a natural log. So notice that because log of 0 is not well defined, it actually returns negative infinite. So infinite is a value you can represent in float. You can actually type in inf. So it could either be just straight up int or np-inf to indicate this is an infinite number. When it comes to computation, we may touch upon this next week, but infinite is not necessarily something you always want to deal with either. It's nice, sometimes it makes sense. In the case here, log of 0 as a negative infinity does make sense mathematically, but this doesn't mean it's a nice thing to handle numerically. So whenever you encounter situations like this, you have to ask yourself, do you really want to get there where you're actually trying to take a log of 0, or do you much rather just avoid it and maybe pad it with the small numbers so that you don't quite get infinite? We'll talk about it potentially next week. Okay, so one thing about array again is also dealing with it if it was, say, a 2D array. 2D array again could be considered as a matrix. So here I created a 2x3 array, or 2x3, what could be thought as representing 2x3 matrix. And one fairly common operation with the matrix is transposition. We basically just flip the axis. So in NumPy, you can actually transpose by saying, taking the name of the array and say dot capital T for transpose, and you get a transpose version of an array. Now this is one of those places where what's returned is not a copy but a view, meaning that if you take the transpose array and modify it, then the original also gets modified. So here I transpose an array, which is this 2x3 array, into 3x2 array, and I index into the last row, first column of the transpose array. So that corresponds to this location 3, and I modify with 100, modify to be 100. If you look at the B right now, it does have that place modified. And if you look at the A, which is the original before the transposition, the corresponding location A has that value changed as well. Yes?
Is there, without checking it like this, is there a way to know if something's a view or a copy?
Very good question. So the answer to all of these lies in the documentation. So this is the thing where you have to kind of learn by checking what are these operations going to perform. Transpose is probably one of the harder one to look up. Let me see if this actually works. Yeah, so transpose is the one that's harder to actually look up. So this is where, and this is going to be something I'll be assigning in the coming weeks, is for you guys to start getting familiar reading up the documentation. I think in the past I mentioned how you don't want to read the whole documentation like a book, unless that's your idea of how you're going to pass time on your weekend. You look these things up, right? So most of the time you can just use these functions quite intuitively and it will behave the way you expect. But from time to time, it's a good idea for you to take that extra minute to quickly look up the documentation and see what is actually getting returned. So I will try to point out as much as possible the common things. So that's kind of one of the purpose of this course is for me to give you the common operations and tell you what is going to give you views and copies so that you can already have a good working knowledge and there should be not as much surprise when you start using these things. But obviously when you encounter a new function you want to use, or just start looking up something and someone tells you, hey, there's a function for that, one of the best things to do is to actually look at the documentation. You don't have to read the whole thing. Some of the doc strings are actually pretty long. But you should probably take a look at it and see at least what it takes in and what it returns. And NumPy being a very open, very big community-based project, it's one of the most well-documented projects. They actually do specify whether what's being returned is a view or a copy. All right, so another very common operation when it comes to working with an array is something we call reduction. It sounds fancy, but all it means is that you take an array and you do something that reduces its size. One of the most common operation being summation. So if I take an array, say going from 0 to 9 again, and if I take sum of it, well, it takes summation operation, and it reduces it into a scalar. So that's why it's called reduction. You now have shrank the size to something smaller. Now, there are two, and from now on we're actually going to see there are a lot of functions that provided by NumPy array that's also available as a method on the NumPy object, array object itself. So the function npSum is also available as a sum method on the array itself. If you were to ask me what's better, there's really no strictly right answer to that. One is not necessarily better than another. But when it comes to being able to understand it quickly or just less amount of typing, you will probably see that a lot of people do prefer to use the method if it's available. So you will see more people doing .sum than npSum of an array. Okay, summation operation just returns a scalar, right? Now it becomes more interesting when you work with something that is not a flat array, not a 1D array, but say 2D array like a matrix here. When it comes to a matrix or like 2D array or higher dimension arrays, you actually get to specify along which axis you want to take the sum along. So just to give you an idea, maybe what's getting represented here is that each row is a person or maybe a animal data, and each column is, say, a spike that occurs over multiple bins. And what you're interested in is per animal, what's the total amount of spikes? Meaning per animal, you want to take the sum across the row. If that's the case, so I'm actually describing the second case, you want to take the sum across the second axis. And just because Python is sticking with this idea that the first is 0, they always count from 0, the second axis, that is across the columns, that's axis equals 1, not axis equals 0. So just to show, if I were to take therefore this matrix of 1, 1, 2, 2 and do sum of axis equals 1, it takes summation across the axis 1. So what you end up getting is 2s and 4. Yes?
Yeah, sorry. So is there a way for you to time your code without it going through the
yeah.
also like printing just
Yes. So I can show you one quickly. So say I want to do it for my sum. You can actually say % time. I think that does it. Yeah, there it goes. So this actually doesn't run it many times. It just times it once. Right? So this is not a profiling. This is just for you to quickly know how long did that operation take.
Wait, did it print out
But it returned the.
oh yeah.
Yeah, I know it becomes a bit cluttered. So another one is, of course, summation across the rows, right? So that you can do by say x equals 0, and here you expect 3, 3. So take some time to make sure you understand what just happened, right? You're taking a 2D array, a matrix, and you're specifying which dimension to sum across. The axis you specify is the axis it visits and takes summation in that dimension. So if you say x equals 1, it goes through the second dimension elements and then sum across them. All right, so then we can see yet another array. And here, there's another operation I'm trying, which is max, which is yet another reduction operation. It takes the maximum along the dimension. And here, basically, I'm saying, give me across different rows, the first dimension, for each of the column, give me the maximum across the rows. So it gives you 4, 2, 8. Should make sense. Now, if I just want to take maximum everywhere, across every element, so you just don't specify axis, and you get 8. Okay? Now, another very, very common thing, and already kind of related to what we saw in terms of sum and maximums, is computation of statistics. So we already dealt with doing this on the list, but say we want to compute the mean. Now, of course, you can take the sum and divide it by number of elements, or you can actually use the built-in mean function. So if you don't pass in anything and just say mean, it computes the mean across all the elements. If it was 2D or higher array, you can also, again, specify the axis along which you want to take the mean. There's also median. So median, interestingly enough, it doesn't have a method associated with it because I guess it's just not that common. They decided not to put in there. So you have to use np.median. So that gives you the median of values. You guys remember what median is, right? It's a 50 percentile. So every number less than that, there are 50% of them, and the number above that, there are 50% of them. And then, of course, standard deviation. So you can do x standard deviation to compute the standard deviation across the numbers. Now, if you've been dealing a lot with standard deviation, you probably know there are a difference between what's known as a population standard deviation and sample standard deviation, where the difference being ultimately, do you divide by the number of elements or do you divide by number of elements minus 1? There's also a way to specify that, and things like that would be a good place where you should look up the definition or you should look up the documentation string. So if you were to do x.std to look at the doc string on the standard deviation, you can say it returns the standard deviation of the array elements along a given axis, and they tell you to actually refer to numpy.std for more full documentation because this is a method version of it. So okay, I want to actually know more full documentation, so I can do np.std question mark on it, and gives you much more descriptive doc string. And here, all I wanted to look at is basically how is it that I can go between sample and population standard deviation, and without forcing you to have to go through it. It's a bit cryptic because they actually use the terminology in terms of degrees of freedom or delta degrees of freedom. Essentially, all they're saying is that if you want to do this n-1 version, which is a sample standard deviation, you have to say DDOF, which is one of the possible arguments, and set it to 1. So if I were to revisit this, if I wanted to do a sample standard deviation instead, I say something like this, and it gives me a sample version of standard deviation. So what I wanted to show is not so much about the statistics or the delta degrees of freedom, but the idea that if you encounter a function, even if it intuitively already makes sense, it's always a good idea to just quickly take a look at the documentation, see what other capability it offers. Okay, so another one, so let's just go ahead and make it a bit more interesting, where we take a bunch of samples. So remember, if I take random.randn, it gives you random samples from the standard normal distribution. So without going into all the details, standard normal distribution means that it should have a mean of 0 and standard deviation of 1, right, among all the samples. 100 samples should be a fairly good number. So if I take the mean across 100 samples and standard deviation across 100 samples, I expect them to be somewhat close to 0 and 1, which it is. Obviously, I get better accuracy or better precision if I actually increase the number of samples. If I take 10,000 samples instead and take mean and standard deviation, I get closer to the expected value of zeros and ones. Okay? So far, so good? Any questions? All right, so the next portion is, well, as I name it, it's the fancy indexing. This is basically a way to say, like, there's more than just that simple index or slice-based way of approaching and getting stuff out of your array. So to illustrate some interesting ones, let's start by creating some array that is slightly more interesting and a bit fancier to begin with. So here, I know this is the first time I'm really showing the capability to create 3D array. Right? So all I've done is basically I just took a flat array that goes from 0 to 12, not including 12, so 0 up to 11. And I just reshaped it, massaged the shape into 2 by 2 by 3 array. One way to think of this is that it has 2 matrices in it, right? 2 of 2 by 3 matrices in it, and that's how you're kind of seeing it. So across the 2, this is the first dimension, and then you have the 2 by 3 array. This way of visualization works for 3D array. You imagine that the moment you actually step into 4D or higher, it becomes harder to see what the structure is. That's the point at which you kind of start to just have to trust what this is, and you just make sure that you know what each dimension corresponds to, because there's really not going to be a great way to visualize anything higher than 4D array. You can always think of this as a group of these things, right? So if this was somehow say 4 by 2 by 2 by 3, it would be 4 of these 2 by 2 by 3, which itself is 2 of 2 by 3 array. So you can imagine you can continue to do it, but beyond 4D, even that way of thinking really doesn't seem to be that helpful. At least you don't really think in terms of that much. So anyway, we already saw how we can index it. And we can also, so if I were to just take the first and just give one number, it index the first dimension. So A0 actually gives me the first index into the first dimension. So it's like taking the first of this 2 by 3 array. If I do 1, obviously it gives me the second of the 2 by 3. And I can just index into subsequent dimension by passing them a comma separated value. So I'm picking the first of the 2 by 3 and then the second row and then third element or third column in it, which is 5, obviously, right? Yeah. Okay, that's fine. That's the standard indexing we've dealt with. Now we get to talk about fancy indexing. And I didn't come up with the term, they actually call it fancy indexing. So one way of fancy indexing, which is actually very, very useful, is by Boolean indexing. So let's just take a quick example. Here I just have an array with some random numbers I threw in. And suppose what I want to do is I want to take all the negative numbers and change it to 0. Maybe I'm just thresholding. Maybe they're not meant to be negative, or I just want to convert it. This process of converting something that's negative into 0 actually has a terminology in, say, signal processing called rectification, in case you're interested in that, or just thresholding. You might have heard that way of saying these things. Anyway, bottom line, I just want to convert negative numbers into zeros. But one way I can do is to actually visit one by one in the loop. So this is actually one thing to keep in mind. So you can just go ahead and visit, right? And then just go one by one and change it if it's negative. So here I'm just stepping through the range of length. So therefore I index from 0 to the number of the elements. So in this case, this is 7 element array. So length of A will be 7. So it will go from index 0 all the way up to 6. So I get to visit one by one. and I ask the question, is that index position array of the array value less than 0? And if it is, change it to 0. Okay, so that modifies the array, and I do get a rectified array like the way I want it. Okay, that's pretty cool, works, but again, like for loop approach, as we already saw, it's not going to be as fast as if there's a way to do it just with NumPy. And obviously there's a way to just do it with NumPy. So first of all, we already saw that we can create a Boolean array by comparison. So we can actually find out in terms of trues and false, what are the places that is less than 0. So I say A is less than 0, and it gives you trues and false, where true indicates that position was less than 0. Okay, so I mean, seems like at least we know where this is. How can we use this information? Well, it turns out that you can actually index with the Boolean array. If you pass in an array of Boolean as an index into the square bracket onto your array, it actually picks only the location where it's true. So if I say A bracket A is less than 0, it picks me all the places corresponding to true. So here, okay, at least I found out who was less than 0 and what value they were. That's still quite not exactly what I wanted. I want to be able to rectify. Well, you're only one step away from it. Now you know how to get to the value. Just like if you can index into it, you can change it. You can actually do the same here. You say A of A is less than 0. It selects those position, and you just say set them to 0. And now I've rectified the array. So this Boolean-based indexing of finding the location that matches certain criteria and then making modification is a very powerful technique that once you get used to, you'll probably be using all the time when working with NumPy.
Is it possible to return all the locations of the numbers that's less than 0?
Yes, so that's a good question. Let me actually give you. So you can actually go, there's a function called non-zero. And if you actually pass in, well, first of all, this actually will give you a location in terms of indices of what are the location that's non-zero. So that's one way to get the non-zero one of those. Okay. You can also take any Boolean. I can leave that. Any Boolean, and if you say np find, oops, no, it's not np find, np where, and then you pass in something like, so let me actually just come up because A no longer contains negative numbers. So maybe I want to find everywhere it's greater than 2. Then it gives you indices that corresponds to where it's greater than 2, return as a NumPy array, which actually turns out to be the same thing as non-zero, I guess. Okay? And the beauty in this is that you can do this on arbitrary dimension. It doesn't have to be a 1D array. So say now I come up with a matrix, or like 2D array, and soon I will stop actually calling these matrices. I'm just going to start calling them just simply 2D array because that's a more accurate depiction of what this is. Whether you're going to treat it as a matrix depends on the context, but it's definitely always a 2D array if it has 2 dimensions. So it's a 2D array. Some numbers are positive, some numbers are negative. Here I say x is less than 0. Again, it gives you trues and falses. Notice that the Boolean that's returned what these comparison operations is always the same shape as the array that went into comparison. And that's important because you can only do Boolean fancy indexing with the Boolean array that has the same shape as the one you're indexing into. So here I take x of x is less than 0 that picks all the location. So return, remember, notice that it takes the position that corresponds to true and just return as a 1D array. That is if you were to use this information. If you're not trying to get the values per se, you just want to index into it, it doesn't quite matter. All you have to say again is x of x is less than 0, set them all to 0. This is rectification now performed on a 2D array. Okay, make sense? Everything good? So there's another scheme of indexing into array, which is called indexing with an array of integer. So let's actually prepare yet another array. So here I'm actually using a range going from 0 to 100, but I'm specifying a step of 10. So it skips with the step size of 10, so I get 0, 10, 20, all the way up to 90, not including the 100, right? If I actually, so let me actually just take a step back before I show the Boolean indexing with the integers. Notice that I could index one at a time. We already saw that, right? If I were to do this, that gives me the 4th element in it. What if I actually want to specify multiple of these locations and get as one list? Maybe I want the position that corresponds to 2, 4, and 5 into a single list. So obviously I can do 2 and then append it to a list, and do 4 and append it to a list, but it's not as convenient. But what you can do is that you can index with a list of integers. In that case, you'll interpret it as, for that dimension, just keep on picking the specified location and then finally return as one array. So if I say return, give me with the index of list of indices of 2, 3, 2, 4, 2, it basically picks the location corresponding to 2 first, 3, 2, 4, 2. So I expect something like 20, 20, 30, 20, 40, 20. And you can just, you don't have to take my word for it. You can just see it, and that's indeed what it returns. The nice thing is you can repeat the same element multiple times. And this becomes useful, say like your array contains different values. And for each of your subject, maybe each of your mouse or each of your human subject, you know what is the index of the value each subject correspond to. And now you're just interested in looking at what is the actual value. Then you can just take the array that contains index into another value array, use that as is to index into it, and you get the values corresponding to each and every one of your subject. Now these, if it's a bit abstract because I'm talking just in terms of words, don't worry, we'll actually get to work with this much closely next week with more real life examples in terms of neuroscience. Okay, so again, you can do 2, 3, 9. That gives you the position corresponding to 2, 3, and 9. And just like with fancy indexing with Boolean, you can also use this for assignment purpose. So if I say 2, 3, and 9, and if I assign -100 to it, well then at those locations the value becomes -100. So notice that indexing and assignment always goes hand in hand. If you can index into it that returns position based values, almost always you can use that on the left hand side of the equal to assign values for that location. All right, so another typical copy is the sort. So say I actually have another array like this, and currently it's unsorted, meaning that the order is not on the particular value, doesn't respect the magnitude of the value. If you call mpSort function on it, it returns a copy. So it returns a new array that has a sorted version, with the sorted values instead. Now, there's a method version of this called .sort that you can call on it. The difference being, though, this actually does it in place. So notice that after I said x and then I get mpSort, which returns the sorted copy, if I look back at x, it's still unsorted, right? It just returned a copy that's sorted. If instead, if I call x.sort, it actually doesn't return anything. But if you now look at the x, it has sorted in place. So this is something you have to be aware of. Sometimes just because you have a function version and method version doesn't mean they're completely equivalent. Sometimes they will use the fact that one is a method and one is a function to do something slightly different. And typically, if there's any difference, it's that the method tends to be in-place operation, and the function being usually a copy returning operation. Now, obviously, that's not always true. Like it didn't apply for mean or max, because there the concept of applying in place doesn't really make much sense. Right? Taking a sum in place doesn't make much sense. You just want to return a sum. But for things like this, where you can imagine it changing the structure of an array, there are typically one version that returns a value, well, returns a copy, which tends to be the function version, and the one that actually performs the operation in place, which tends to be the method version. Again, something you do want to look at the documentation unless you're pointing out like this. Now, for higher array dimensions, you can actually sort. So if you think about it, if you have 2D or higher, and if I tell you to sort it, there's no clear definition what it means to really sort it. Right? I cannot just sort a 2D array. Like you have to really kind of decide what that really means. When the more, at least a consistent approach towards it is that you sort along a dimension at a time. So here you can again specify an axis to sort along. So if I were to say sort A along the axis 0, it sorts along the first axis, which is along the rows. So you can imagine if it's going to sort like 131 into probably 113, 892 gets sorted into 289, so on and so forth. And you can verify that's indeed what you get. And just to sort out alternative, you can sort along the columns, and you probably get something like 1458, 2349, and that's what you get. Okay. Remember, I'm using the sort function, so this returns a copy. The method actually also can take an access, but in that case, it will sort it in place. All right. So there's one thing I actually kind of been like using it without really warning you about it, is this concept of keyword argument. So I think this is a time where I probably should really try to visit it. So you saw in means and max and also sort that you can sometimes pass in arguments by specifying a name equals something. These are actually called keyword arguments. And it's not just special to NumPy function. It's actually something you can use for any functions. In fact, even the functions you define. So let me actually show you an example. If I were to show you a function like this, a greeting function, which takes name, message, and n, you at least show that where you're seeing the fact that when I give values like that, that's a default value. Meaning a person can call this function without specifying the second and third argument. If you didn't specify, it would just default to whatever you put here. Because the first argument it doesn't have a default, this has to be always be given. So if I just call it one argument alone, it will use message hello and n. So here it just repeats the message n times, with the message itself being hello by default, followed by the name of the person. That's what all this code does. So here if you just say Edgar, it will say hello Edgar. If you give the second argument, this replaces the message. So you should say morning Edgar once because n equals 1. And finally, if I actually just give the all three values, this repeat the morning Edgar message 10 times, right? Just to be annoying. Now, what if I'm happy with the default message? I'm totally fine with hello. I just want to repeat that message 5 times. If you were to just specify things by position, you really cannot specify the third argument without filling in the second position. Well, thankfully, there's a way to just jump to the argument you want to specify by specifying the name of the argument, in this case n. So if I say Edgar and then n equals 5, it will overwrite the value of n by 5, but since I didn't say anything about a message, it will keep the default value of message, which is hello. So in this case, repeat hello Edgar 5 times. And this is actually all there is to it in terms of keyword arguments. Basically, if in the definition of a function you give these names, this is actually the name by which you can pass the values. So you can either specify an argument by position. In that case, it would just respect the order of the arguments. Or you can just straight up give the name equals to a value, and you can actually ignore the ordering. And in fact, you can actually totally ignore the ordering on something like even the first one. So name doesn't even have a default value, but you just have to make sure you just give it, right? It doesn't mean you have to always give it as the first argument, as long as you somehow give it. So here, I'm actually totally swapping the order around and say n equals 10, and since I know I have to give the name, I'm giving n name equals John, and they'll happily use that. And I can totally mix and match position, the keyword arguments in any order I want, as long as they're given. Okay, so that's all I wanted to say about this. When you say axis equals to 0, all that was doing was that, well, it was one of the arguments for that function that you're specifying now directly with a keyword argument. And the reason we were not just saying something like mean x comma 0 was that to be explicit, what does that 0 would mean? We actually mean x equals 0. But in the future, you will see that there will be function that takes actually many, many arguments, potentially, but most of them being optional. In that case, if you just use position to get to the argument, you have a lot of things that you have to specify before you can finally specify the real thing you want. And usually, what you want to, all the things you have to fill to get there is something you don't really want to touch. So in that case, you just use keyword argument to just jump to the argument you want to change and specify, and that's what you do. And we'll see a lot of this, especially when we actually get to plotting, which is coming up in a couple of tens of minutes or so. All right, so far we've covered quite a bit of NumPy array. How to define it and how to create it, that was the topic of last time. And this time we really looked into how to use NumPy array by defining how you can add, subtract, do multiplications, and also call functions on it, and also look at some of the fancier indexing, such as Boolean indexing, which actually becomes bread and butter for day-to-day operation when you really work with NumPy array. There's one concept I must cover, and this is probably going to be, depending on your background, could be a bit weird. And when I say that, I don't mean as in like if you're inexperienced, it's going to be weird. It's more other way around. if you already have experience with packages or languages, say MATLAB, this will feel weird because it actually doesn't quite work the same way, say how MATLAB works when you actually try to add two things. So without me trying to just say it, let's just look at it. So far we actually already looked at if I create two arrays of same size, right? Say here 1, 2, 3 and 1, 1, 1. And if I try to add them together, it just happily does an element-wise addition, right? And this is exactly what would happen if you were to add two vectors in math. So nothing should be surprising here. Now, one thing I haven't quite covered is that 1D array really doesn't have a dimension beyond the first, right? So that's like almost given when I say 1D. But what I really mean by it is that if you're familiar with the concept of column vector or row vector from math, where like a vector could be sideways or vertical, that actually requires you to have at least two dimensions if you think about it. If it's only one dimension, there's no way to swap the dimension. Everything is laying around just the only one dimension that exists. So if you ever want to have a concept of a column vector, or row vector even technically speaking, you actually have to have a 2D array that is of specific dimension. Meaning that if it's a row vector, it's actually a 2D array of 1 by n shape, and column vector is n by 1 shape. So for example here, if I write it like this, notice that this is the same list of lists except that each row is one element. So this is my way of specifying a column vector, right? And notice that in order for this to be a column vector, it has to have an ndim, the dimension of 2, and its shape is, oops, what did it say? Not n, sorry. Its shape is 3 by 1, making this a column vector. Now, again, if it's a column vector and they're both two column vectors, adding them is not an issue, right? If I just a plus b, it just does a corresponding location, just like we were able to add same size matrices element-wise at a time. Mathematically consistent, any mathematician will approve of this, you're totally good to go so far. Now it becomes really funny if you have a row vector. Here, notice that I actually did define this as a 2D array row vector. Right? So it has a shape of 1 by 3 here. And a column vector, which has a shape of 3 by 1. It becomes a question, what happens if I add these two together? Now, those of you who are pure math would tell me that's an invalid operation. You cannot add matrices or vectors of incompatible shape. Yes, that's what math would tell you, but that's not what NumPy would tell you. If you add a plus b, you get a 3 by 3 matrix. A 3 by 3 2D array. Okay, so it's obviously not obvious, right? So let's actually visit to think about what really just happened, right? And if you want a one-word answer, what just happened? Well, broadcasting happened. This is what a broadcasting does. So in order to truly understand it, you have to think in terms of how could you actually arrive at this, right? Let me actually see if I have a better example on this. No. Yeah, so I meant to just explain it in place. So what really happened is that you were taking a 1, 1, 1 column vector and 1, 2, 3 row vector, and because they're incompatible in shape, one is 3 by 1 matrix, or 3 by 1 a 2D array, and one is 1 by 3, they seek the closest middle ground by actually just increasing the dimension of what's the one that has a shape of 1. So if it's 1 by 3, what they do is they just replicate it 3 times to make it into 3 by 3 array, by repeating the same thing. So in this case, you can imagine that this 1 by 3 will turn into a matrix 2D array of 3 by 3 of size of the content 1, 2, 3, 1, 2, 3, 1, 2, 3, just repeating it. And similar thing happened with B. It just got repeated 3 times now along the columns. So in this case, since it's 1, 1, 1, it just filled the entire thing with 1. And now you have two compatible shapes, 3 by 3 arrays adding to each other, and hence you get 1, 1, 1, 1, 1, 1 array adding into something that's 1, 2, 3, 1, 2, 3, 1, 2, 3, which results in, well, 2, 3, 4, 2, 3, 4, 2, 3, 4. Another way to think is just if you have two arrays like that, it just basically sweep through and sweep through each other. That's what essentially broadcasting does. So if you want a really technical definition of broadcasting, it's basically repeating of the dimension, or repeating of the shape in the what's called singleton dimension. Basically, dimension along which the shape is only 1. So if it's 1 by 3 array, this first dimension is a singleton dimension. The shape is 1 there. So it will happily repeat along that dimension to change the shape if that's what it takes. So if you try to add 1 by 3 and 3 by 3, the only compatible shape you can achieve by repeating along the ones is 3 by 3. So that's what they do. They change both of them into 3 by 3 array, so now you can do addition with each other. Following the lecture, I will actually point you to a good reference. There's actually a good resource that has more pictorial view. I just didn't want to copy and paste. I just felt like I'll just give you it so you can look at it more pictorially. But that will give you more like visual perspective of how is it that this broadcasting works. Now, just to wrap this point up, when you work with broadcasting, the shape starts to really matter. Like you actually care about now the existence of singleton dimension and the fact that if the two shapes are not matched up, at least one of them has to be 1 so it can be repeated to match up in shape. So if that's the case, you need to know how to really manipulate the shape of an array. We already talked about reshaping, right? You can reshape an array by calling reshape on the reshape method on it. But it also becomes important that sometimes you just want to flatten an array. You can actually flatten an array. So say it's a 2 by 3 array like this. You can convert it into a flat array by calling the function rabble on it or method on it. And you can look at that. It actually now has become a flat array. Now this returns a view. Rabble by default returns a view so that if you modify it, the original gets modified in the corresponding location. The problem is, what is the corresponding location? So in NumPy array, when you flatten an array, it actually visits last dimension first, right? So in this case, it would actually visit along the rows first and then columns. And if you had higher dimension, it would visit along the higher dimension. So this just meaning if you flatten an array that looks like this, it will go 1, 2, 3, and then next row 4, 5, 6, resulting in flat array of 1, 2, 3, 4, 5, 6. Obviously, I shaped it in such a way it's easy to tell, but once in a while, if you have more complex content, it might not be the most obvious thing. So this is something you should really practice and think about it with an easier array, just to make sure that you understand what is the order by which elements gets visited when you flatten an existing array. Okay. This becomes useful, as we see actually shortly for plotting, if you want to just visit every element of an array. You just turn this into a flat array by rabble, and you can treat it like a list where you can now iterate through it. It becomes an iterable object. So you can happily say for x in x.rabble, or for x in array.rabble, it becomes a flat array, and x just now visits one element at a time. All right, does that make sense so far? I know the broadcasting probably kicks you off a bit. That the reason I'm also not stepping into too much detail at this point is that broadcasting is something you really get once you really need it. I could spend like tens and 20 minutes on talking about broadcasting, giving all sorts of examples, but unless you really need it, you're not going to really get it, right? So this I earned the side of just kind of introducing the concept. And then hopefully, especially next week, as we really start to do computation, you will see why someone would even dream of using something like broadcasting. Now, for those of you, and this is the one I just wanted to say, for those of you who are already familiar with MATLAB, you're in a bit funny position. MATLAB has an element-wise addition, right? You're probably familiar. You can do dot plus, dot multiply for element-wise multiplication and addition, because otherwise they will try to do what's more consistent with the matrix. So if you do multiplication in MATLAB, by default it does matrix multiplication. And if you try to make MATLAB do addition of two matrices of incompatible size, they will complain saying this is incompatible. Until 2017, that was the truth. Starting from 2017 B version of MATLAB, they now do broadcasting. So this is just to warn you, very likely you're not using the latest version of MATLAB, so hence broadcasting is not how things work. There's actually a function that lets you do broadcasting in MATLAB, but it's a special thing. But given the popularity of packages such as NumPy, they have stepped towards the direction of letting broadcasting be the default. Usually this is okay, except that it's not okay because people are not used to this and they haven't been coding with this expectation. So I'm just wanted to put that warning out because this is actually something that's been causing decent amount of issues among MATLAB programmers because now broadcasting is a first class citizen in MATLAB. But that being said, at least you should take that as some sort of confirmation that broadcasting appears to be useful. Otherwise, why would MATLAB implement it, right? All right, so reshaping we already visited in the past. You can take a, say, flat array going from 0 to 23 and reshape it. You can reshape it as long as the shape, the new suggested shape, matches the number of the elements in total. So since I have 24 elements, as long as the shape multiplies the total number of elements of a new shape is still 24, you can reshape it. So 2 by 3 by 4 is totally fine, right? It still has 24 elements in it. So this is also a good exercise to see whether this reshaping made sense. Again, when you reshape, it always goes last dimension first. So it takes 0 to 23 sequence and lays out in rows first, or the last dimension, along the columns first, but last dimension first. So it creates 0, 1, 2, 3, that's the last dimension of 4. Then next one, and next one, until you now have 3 by 4. And now you do the first dimension, there's 2, so now just repeat it again. So this is how you get 2 by 3 by 4 array. All right, and okay, another thing is that you can actually take an existing array that's not flat and turn it into another shape. Again, as long as the number of elements matches. So here I have 4 by 3 array, so that contains 12 elements. I can shape it into 3 by 4, no problem. I could shape it into 6 by 2, that's not a problem. Only thing is, again, just be aware of the order by which they reshape it. If you really think about it, the way it works is that it first takes the array, flattens it, and then reshape it into the final shape. So just because 4 by 3 and 3 by 4 looks like you could just transpose one to make that shape, doesn't make NumPy do it. NumPy wouldn't transpose it for you. You'll flatten it and then reshape it. So just notice that these two are not the transpose of each other. All right, and I think that's the last point in this notebook here is adding and reducing dimensions. For the sake of broadcasting mostly, you once in a while want to add an additional dimension, right? For example, it happens if you have a row vector and now you want to turn it into a column vector. Row vector, well, you have a 1D array and you want to turn it into column vector. But since I mentioned that column vector only exists if it's 2D array, you have to somehow take a 1D array and make it into 2D array. 1D array, say, had a shape of n, and now you want to make it into n by 1. There's this additional dimension at the end. You can actually add a singleton dimension with a particular trick, which I'm about to show. So here, just to motivate the problem again, say I have x and y's. There are two arrays, and they're both 1D array. So shape is 3, and 4, indicating it's a 1D array of shape 3 and shape 4. Given that they're in the same dimension and there's no dimension along which they can replicate, there's no singleton dimension along which they can replicate to get a agreeable size. There's no way to replicate shape of 3 and shape of 4 to make it compatible with each other. So if you try to add them together, it wouldn't actually work. And it will say you cannot broadcast these two shapes together. Okay. So one way to deal with this is to make, say, one of them into column vector and one of them into row vector, such that they have a singleton dimension that could actually then replicate and broadcast, just like how we saw it earlier. So of course you can create that from scratch, but you already have a data and you gotta turn this into the right dimension. You can actually add a new dimension by using NumPy new axis when you actually index into something. So this is a bit funny notation, but say I'm taking x, and what I want to do is add a at the beginning, an extra dimension. So I want to turn this from shape of n into 1 by n. So there's extra dimension at the very beginning I want to add, and the way you can achieve that is by placing np new axis at the beginning, comma separated by column, which selects the rest of the elements. I know this is a funny notation, but this is a way to say that I'm adding a new dimension at the beginning. And now it is now turned into 2D array, and if you look at the shape, it indeed has now 1, 3 shape. So applying the same idea, now you can also add dimension on the trailing side of things. So if you have a shape of n, which is a flat array, you can turn it into column vector, which is again n by 1. So you want this extra 1 dimension at the end. Well, you can do that by say y colon comma np new axis in a square bracket that changes its dimensionality into now 4 by 1 array. This is something I will suggest that you look over this notes a couple of times later again, because this is something that takes just some time to get used to. And as I also said earlier, it becomes even more like it really starts to sink in once you really start using it. So if this doesn't all like sink in immediately, it doesn't feel immediately intuitive, don't worry, it's not supposed to. Okay, now you have singleton dimensions, right? You're trying to add 1 by 3 plus 4 by 1 shape array. There's one in place where you don't in mismatching position, so it just turns the 1 by 3 into 4 by 3 and 4 by 1 into 4 by 3, so you can finally add them, replicating the dimension as necessary to get this result. Okay, I'll let you go again to see if this really makes sense. So this is something you want to go over a couple of times, and again, I'll provide a resource which gives you a bit more visual overview of how the broadcasting works. All right, and finally, just like you can add a new dimension, you can always remove a dimension as long as it's a singleton. If you really think about it, if those singleton dimensions, so when I say singleton dimension, that means a dimension in which there's only one shape of 1, right? That is a bit of extra shape. 1 by n could have very well easily be expressed by shape of n. 1 by 1 by 1 by n could have been just shape of n. 1 by n by 1 by 4 could be n by 4, right? So those extra dimensional shape 1, those are called singleton dimension, can actually be dropped without losing any content in your data. And that's what sometimes you want to achieve. So here I have an array that's 4 by 1 by 1 by 3 by 1, which obviously only have 12 elements in it, but if you look at the structure, it looks pretty complicated. Right? There are 4 of 1 by 1 by 3 by 1. And for each of this is 1 of 1 by 3 by 1, which is 1 of 3 by 1 array. Yeah, I'm not gonna really go and repeat this over and over, but you get the idea, right? You would think like, well, element-wise, shouldn't this just be 4 by 3? Isn't it much easier to look at it? Dimension sometimes matters. Actually, it does often matter. So just saying like, well, it has 12 elements, so it should be 4 by 3, or actually just 1 by 12, is not going to quite cut it, right? That dimension might mean something. Maybe it's indicating the fact that this was, I don't know, maybe this was like a 4th person in your lab on their first month, the first day, third mice, the first recording, whatever that means, right? But dimension usually does have a meaning, meaning that you cannot usually just drop it just because it's 1. But when you work with it once in a while, you do want to drop it. So you can take a 4 by 1 by 1 by 3 by 1, and you can squeeze out the singleton dimension by calling squeeze on it, which returns a copy. Oh, sorry, which returns a view. Not a copy, my bad. Which returns a view which now has all the singleton dimensions squeezed out. Okay, so you can imagine really taking this like unnecessary bloated in dimension array and just like packing it into what it has to be, so to still be able to represent the data.
Does MATLAB have something like this?
Yes, MATLAB actually have a function called squeeze as well. Yeah. So okay, the reason MATLAB comes once in a while when I talk about this is because there's a lot of like intellectual exchange between MATLAB and NumPy, namely MATLAB being mostly the first. Right? Now MATLAB has been in existence for actually quite a few decades by now, and it has really set for a good example of how to work with something like matrices or even higher dimension structures. So there's a lot of concepts borrowed from MATLAB when it comes to NumPy. But there's also a lot of new things that NumPy decided to do in their own way and things they decide to do differently from MATLAB, which makes it useful but also makes it a very torturous exercise for those who have to work with both, because there will be a lot of similarities but subtle differences that once in a while you forget. For example, index of 0 versus 1, right? But anyway, it's always kind of, if you know both, it's nice. Just, you know, it might take some switching back and forth might not be the most straightforward thing. All right, anyway, so that's the end of this notebook, and these are sequences of exercise. If you already haven't done this, some of them you really could have done from last session. Many of them, I think, use this information starting with this. Is that true? I think I mostly kept this so you can do most of these from just what we covered last time. So 8 in particular, last one in particular, definitely uses broadcasting. So if you want to tackle this problem, you should try this. So I recommend that you try this. I will upload the completed version of the notebook. That means I'll add it to the GitHub repository and notify you guys so you can always do the git pull upstream master to get the answer sometime probably over the weekend. Okay, but it's something you should try to get to. Okay, so that's with NumPy, right? And that's not the end of the session today. We have one more topic, and actually a much more visually appealing topic of plotting. So now if you go to notebook 4, which hopefully should be there because you did do the git pull upstream master. If you haven't, this is your chance to go into the terminal, go to the folder that contains the repository, and run git pull upstream master to get the latest updates from the upstream repository, which is Edgar's guide, Python Neuron course. Yes?
So if we do get pull upstream master and we pull like the third notebook with the completed exercises, we're gonna have our version of the notebook. Can we?
So yeah, the one is that that's not going to happen because I'm not going to put it in place. Yeah. So what Stelios was referring to is this idea of like what happens if like now guys open up and you already ran some stuff, so you change the notebook, and say you decide to commit it because you actually did a couple exercises now, and actually you say you did the exercise, so you actually have answers in it, you want to save it, and you being a good Git citizen, you actually add and commit. You guys should be adding and committing, right? Especially when it comes to homework, which I'll talk about today. But now you made your commit with some changes, and say later on, if I were to put my answers in the very same notebook upstream, if you now then do git pull upstream master, you have a conflict, right? Because Git would be wondering whose answer they should respect. Of course, mine, but well, not really, right? You don't know whose answer should be respected. There's no right answer when it comes to merge conflict like that. So when it comes to that, you have to go through a bit of exercises and looking at what are the two changes and selecting out one at a time. Quite a mess. One day you probably have to deal with it, but by the time you have to deal with it, hopefully you're better equipped and better exercised in Git, because it means that you're working with someone on a project. But for the sake of this course, and because we are very well communicating with each other, I wouldn't do that to you. Basically, if I were to come out the completed version, I'm going to create a whole new notebook with the answers in it in a completely different place, so there's technically two unrelated notebooks. And that will be inside the completed folder. Okay? So when you work with others, like, if you talk to some people have got burned with Git merge and merge conflict. Admittedly, it's one of the most difficult and potentially annoying problems with Git, but it's not so much a problem of Git if you really think about it. It's actually a problem of miscommunication among people working on the same project. So don't blame Git, it's blame someone else or blame the fact that you haven't communicated with each other. If you run into a lot of merge conflict with each other, no, it's not a Git issue. It means you guys have to talk, right? And I stress this point because I actually do get this complaint like, oh, I don't like Git because I run into this merge conflicts and it's a huge mess. It's like, yes, it's a mess because it's a mess in your collaboration scheme, not the problem of the software. Okay, but since we are communicating well, I wouldn't do that to you. You should be fair. Okay? All right, so I'll open up the fourth notebook. This is called Plotting with Matplotlib. Now finally things are getting more visually interesting. We learned so far to represent data in arrays. Well, not really data. We haven't really visited real data, but at least conceptually it represents something in arrays and do computations on it, manipulate the arrays. We even covered the topic of broadcasting. It's all good. It's all nice. You can compute stuff with it. But that's only half the story when it comes to scientific computations. You have to somehow look at your results, understand your results, and oftentimes this means you have to visualize your results. So plotting and visualization is actually a huge chunk of scientific computation. If you really think about it, when it comes to manuscript publishing, that's how you tell your story. That's how you tell your result with people. So plotting is exceedingly important. So if you must choose a language for your scientific computation, going by a language that provides a very solid plotting library is actually not a bad idea. And I'm happy to say Python does come with a very solid plotting library, and that's called Matplotlib. Just like NumPy, it's a package. It has a lot of things in it. It has many modules with a lot of code in it, so you just have to import the package to be able to start using it. MATLAB is so big to the point it has a lot of packages and sub-packages. So when you actually want to work with them, particularly for this plotting purpose, what we're going to do is we're going to import its sub-package called pyplot, and import it under conventional name PLT. So this is what we're doing here. You're importing matplotlib.pyplot, which is a sub package inside matplotlib, and I'm importing that under the name PLT, following the convention. Now there's one more line I'm adding which might seem very cryptic, but maybe you can start to guess this is, yes, a Jupyter Lab related functionality because it starts with a percent. Just like we use percent time and percent time in, percent is a directive or a command to the Jupyter Lab to tell them to do something. Jupyter Lab and Matplotlib has been living so close to each other, they are aware of each other. So what we're doing here is by saying matplotlib inline, we're saying every plot we're going to make using matplotlib and Jupyter, I want it to show inside the notebook. If you don't do it, what could happen, depending on your setup, is that every time you plot, it spawns up a new window somewhere with your plot. This is fine. Sometimes that's what you want. Most of the time, you just want to see it directly inside the notebook, so you can also save it. So run that command once, and you should be good to go. And just because we learned a lot about NumPy, we obviously want to use it, so we're going to import NumPy as NP following the convention. Okay, so without further ado, let's just go ahead and plot stuff. And I couldn't really come up with anything simpler than plotting something like y equals x, a line. Well, what you can do is say I define x. Remember in linspace gives you starting and ending and just equally spaced points in between until you get the number of points you want. So here I'm telling go from 0 to 5 with 3 points total, which means 0, 5, and something in the middle. 2.5, right? And my y equals x. So I say y equals x. And I plot the x against y. If you run it, you should get a very beautiful line. Right? You probably couldn't be happier when it comes to line. Okay, cool. Yeah, you got a line. Okay, so what really just happened? You obviously use this function called plot under the PLT package, which we imported. And this is one place, again, like when you're encountering a new function, go kind of take a look at the documentation. So if you do plt.plot, you get a docstring. And it's a long docstring. It has a lot of things packed into it. Obviously, I expect you to know every single line of this by the end of the course. I don't know every single line of this. It has a lot of functionalities, and just like I said, like this is not something you just read in whole and then try to memorize. Like you really never ever do that unless you're the developer of the package. Then everyone can expect you know every single line of your code because that's what they just come to expect. So unless you wrote that thing, it's totally fine for you not to know everything about it. Just know enough to be able to do stuff with it, right? So obviously this is pretty long. I'm going to here go and shrink it. So in case you guys haven't figured it out, if you actually click on the bar here, it collapses the thing. Okay, the most important statement, at least to my mind, in the plot document docstring is the first line. It says plot y versus x as lines and or markers. Okay, fair. So basically plot sequences of coordinate points x, y, connecting them with straight lines by default. That's what it really does. Okay, this wasn't really obvious when we plotted a line because everything is a straight line. So let's actually see the case. What happens if you plot something a bit fancier, say like y equals x squared, a quadratic function. Again, I go from 0 to 5, 3 points, right, with the linspace, and I say y equals x squared, and I plot it. And this might not be exactly the quadratic function you're used to seeing. It looks a bit, I don't know, kinky, right? It has a kink in it, and if someone tells you, hey, this is how quadratic function looks, you should really start to doubt their mathematical capabilities, right? Of course, that's not the problem mathematical capability of NumPy at least, or matplotlib. It's just that you only use 3 points, right? When you're plotting in NumPy with plot, you actually are plotting points. So this is one thing I want to stress. You're not plotting a function per se. It's not like one of those things where it just takes a function and gives you a perfectly nicely smooth curve representing the function. You're really taking values from a function and plotting by connecting some sample points. So, well, that's, and you can verify the fact that, well, my x was only 3 points, and I have a corresponding values of y, which is x squared, for those 3 points. I'm trying to represent x squared with 3 points. What you should expect, it's going to be not a smooth curve. So, of course, if I want something much smoother, the solution is to simply increase the number of points you use to plot it. So earlier I was saying 0, 5, 3 to represent with 3 points. Here I'm just going to go with 100. You hopefully see why I'm using linspace. Linspace lets you say the end and start and the end and fill it with as many points as you need. and becomes a very, very convenient thing when it comes to plotting. So here I'm using 100 points instead, and now the curve looks much smoother because you have 100 points to represent your curve. Okay, well, so that's cool, but you know, this is the only thing it can do, then that's not as exciting. So there are obviously many more things you can customize about this. So one thing you can customize is the line and marker styling. And one of the most common way to do that is by passing a third argument, which is going to be a string that contains certain keywords to indicate how is it that you should be plotting it. So if you pass in the third string with O, it plots just the points as dots. Okay? Here basically it's no longer connecting them, you're just seeing the pure data points. If I want these dotted dots indicated but still connected with a line, I say O dash and I get dots connected with a line. Now say I didn't like O but I just want to see the line, but say I actually want it in dash line, I say line dash dash and that plots it in dotted line. And last but not least, I actually want the markers to be something fancier, like a diamond. Then I say D in capital dash dash, and I get the markers drawn as a diamond shape. Now this is not the end of it. There are far more than this, and I have linked you to a documentation of Matplotlib. And this is actually my initiation for you to start looking at documentation, at least the relevant pages and the interesting ones. So here, if you click on them, you don't have to do it right now. Here, if you're to click on it on your free time, you will be taken to a page from Matplotlib that explains the choices of markers that exist and choices of lines that exist that you can combine to achieve the styling of the lines and markers. So when it comes to plotting, and in fact any other library, this is how you tend to operate. You just go, use the basic functionality, get 90% of what you want, and then at the last 10% you achieve by actually starting to learn more functionality of the library to really get what you want. And when it comes to plotting, there's a lot you can customize. And to some extent, that this really comes with just trying a lot, doing a lot of experience, with getting a lot of experience, and just bothering people or looking at people's plotting code to be an expert at this. But I can tell you, it's worth it. Right? When it comes to manuscript publishing, we're just trying to show a nice plot. Like how nice your plot might not quite change the content of the plot. It's not going to suddenly change your data and make negative results positive. Obviously, if you did that, there's some fraud going on, right? But how you tell, how you show your result really matters. It makes how intuitively understandable. It changes how intuitively understandable it is to people, and it can make your point very clear by coming out with very cleverly designed plots. So investing time into coming up with a good plot is really worth your effort. At least that's what I want to say. And one nice thing about Python is that if you really learn it to do well, you can get to the point where the plot you get immediately out of Python is a publication quality plots. You can actually just take it, maybe do just a tiny tweaks, and it's already ready for publication. And that's not necessarily true. I know I'm going to get disagreements from this from some people. It's not necessarily true for something like MATLAB. MATLAB has a lot of plotting capability, but getting the last tick mark in the right position can be a lot of effort, which is not hard in Python. So that's actually one reason by which I do every one of my plotting in Python, despite the fact I actually have projects that say it's heavily MATLAB based or interoperating between two languages. All right, so that's just my pitch talk for Matplotlib. I hope I get paid by them someday. Right, so adding more information to your plot. So obviously you want to have more and more stuff, right? Like what about labels? What about the titles? Well, you know, you have that. You can add that as well. So here I'm also like combining with the fact that, well, if I get a bunch of data points like x values, I can compute something like cosine curve. You know, just like because everyone loves cosine curve, obviously, right? So here I'm actually saying angles is anything between -2 pi to 2 pi, right? So spans 2 full cycles. Am I reminding you of the physics class? NP cosine of angle computes the cosine of the radians. Right? So I get the angle value pair in plot. And just to make sure that people get the idea that the x-axis is my angle and y-axis is some value, I'm going to label it with x label and y label. And also I'm going to put title just so you know this is the trigonometric function I'm plotting. And this is what you get. So you get an x-axis label and y-axis label because of usage of x label and y label. And you get a title with the title function, trigonometric function being the title for this plot. Make sense so far? You can obviously plot multiple lines. You're not limited to one line per plot. You can just go ahead and plot multiple lines by just calling plot a couple times. So here I'm actually preparing cosines and sines. Notice I'm using the same angle as my x, but I'm just computing cosine values and storing as value 1 and sine values storing as value 2. This is not going to be quite a descriptive name. It probably would have been better named something else, but here I'm not being that creative. I'm plotting angle against value 1. That should be my cosine curve, and angle versus value 2, and that will be my sine curve. And nicely enough, Matplotlib will color it differently when you plot multiple functions with plot. So at least you can tell that there are two functions getting plotted here. Of course, the issue is I don't know which is which. Well, I do know which is which technically, but it's not obvious, right? So this is where you want to put legends in, right? Well, there's a plot.legend. So let's go ahead and put plot.legend. What I did is just put the plt.legend at the very end. Let's see what we get. Now we don't get anything new. It complained that no handles with labels found to put legend on. This is really Matplotlib's way of saying, you didn't tell me labels. So you have to label your plot if you want the legends created for it. Okay, fine. So we can put labels on it. In the plot, I put this extra keyword argument called label. And I'm just going to label it. Here, at least I'm hoping I'm labeling the right one. The first one I'm saying this is a cosine of x. The second one is sine of x. And now legend will happily take labels of the plots and create a legend at the corner. And there are many more things you can control. If you were to look at the doc string of the legend, it will tell you how you can tell them to position the legend box on the top right corner instead of the bottom left corner, or put it wherever you want. You can be arbitrarily. You can even place it outside of the bounding box. I'll leave it to you to explore. So we already kind of been looking at the keyword argument. That's one of the theme today was like you can customize behavior in many things by passing in arguments, and namely keyword arguments. Again, keyword argument is the better option because oftentimes there's just so many arguments in, you don't want to positionally specify. Otherwise, you have to specify a lot of things you don't care to specify. Keyword argument really lets you jump to the thing you really want to specify. So one of the nice things, for example, you can control would be color. I mean, they decide to obviously color it some way. So this starts with blue. The next line tends to be the orange. So Matplotlib has its own default of what are the colors it uses if you keep on plotting it. But you don't want to be always told what to do. You want to control what you do. So here I love red, so I decided to color my curve red. And I achieved that by saying color is red. Color actually takes in many other ways of specifying color. Red as a string being one option. You can also pass in hexagonal values, like if you're familiar with the specification of RGB spectrum. There are many ways to specify RGB, red, green, blue mixture, to get any colors you want. And it takes it. I'm not going to really go over it because it's a fun, but not intellectually stimulating exercise. So you're more than welcome to look up the Matplotlib's documentation, either on the plot itself, or if you just look at Matplotlib color, it will tell you on Google, it will bring up a page suggesting what are the ways by which you can specify color. If any of you are familiar with XKCD, how many of you are familiar with XKCD? Yeah, it's a comic strip. Basically, they make fun jokes about science and statistics and computer science, and often they are very good, very to the point. And one of the things, though, that author really does is also trying to make contents accessible. And one of the efforts was put together by them, or actually the author mainly, is to come up with the common names for color that's just we see all the time. So he basically came up with, I forgot how many, like 300 or so different color names under some common names. Like teal, like dark brown is now officially a color name. Like serpentine or something like that, coral red. There are many, many color names he came up with when he actually surveyed to get common color names. So that's actually one way by which you can specify. So bottom line being, there's many ways to specify colors, and some of them being more interesting than just having to say red or RGB values. You can also change the thickness of a line by using the keyword argument line width. So here I'm making it thicker because this is a very important figure. And finally, you can change, finally being like at least among the final ones I'm showing right now, you can change the marker. So you already saw you can pass in third argument of string to control the appearance of the markers and lines. More keyword argument way of doing that would be to pass marker and just the marker related specification. So S will give you a square, right? And I say I want it bigger. Like this is just not cutting. I want it bigger. It has to be emphasized. Well, I'm going to give a marker size argument as well and make it big, like 10. So you can see that with the usage of keyword arguments, you really can specify a lot of things. And this is just looking at one line being plotted, right? Now there's obviously things you can change about the axis, the environment in which this is plotted as well. So here, if I were to just plot this, so here I'm actually coming up with a slightly more complicated function. I'm actually defining a polar whirl. I'm not really going to step into how this is defined. I'm going to actually show exactly how I came up with it. So it just kind of whirls around. It's actually whirling from inside out if you really look at how the way it's being plotted. Anyway, it's a whirl. Well, so no, it plots it, it's roughly fine, but say I actually wanted this to be absolutely centered, like I know it starts at 0, 0, I want that to appear right in the center, and because of the way I define, I know the bounds are perfectly -1 to 1, -1 to 1 in both dimensions. So I want the bounds, the x bounds and y bounds to be -1 to 1, and you can control that with x lim and y lim. So I control that. Okay, now it's -1 to 1 in both, exactly. And now I'm not a huge fan of the fact that it has so many tick marks. I feel like this is just aesthetically not pleasing. So I want to control the tick positions by using x ticks and y ticks, passing in the list of tick values. So here I'm giving -1, 0, 1, the list, to specify that's exactly where I want my ticks to be placed. This is now what I get. So pretty good. I'm getting closer to what I wanted to see. Lastly, I actually want to make sure this is correctly squared. I want both the x width and height to be at the same because it's supposed to be a perfect square, and that you're controlling aspect ratio. You can control aspect ratio by using axis and passing one of the predefined values to indicate what is the kind of aspect ratio you're talking about. Here it takes an argument called square to make sure it plots it as a square, or at least the same unit when it comes to x and y axis. Okay, so I'm pretty happy. What's the last thing I said? I almost can swear there's one more thing I thought I added. No, I think this is a duplicate, sorry. I just plotted just to make sure. Did I change anything? No, this is a duplicate. All right. Okay, so far so good. So the whole point being there's a lot to be controlled, and I'm not going to obviously go through everything today. There are just way too many things. I'm still learning day by day, but at least what I'm covering is very good starting point. At least you can already start to plot stuff. Now, sometimes what you want is one figure to contain multiple panels. In fact, in pretty much many journals nowadays, you'll always end up having that, right? And they're supposed to kind of tell a story together. You can do that. And this is one way of doing it. We'll revisit another way, which I think is a better way. And here's one way to create what's called subplots, basically plots within a figure, like smaller panels within a figure. Otherwise, one plot occupies the entire figure. Here you're just basically having multiple panels. And you specify that by saying subplot, and you pass in 3 numbers. The first number indicates how many rows of subplots you're going to have. Second specifies how many columns of subplots you have. And then third number is where in this row-column combination you are at. This is where it's going to be a bit confusing because this starts counting from 1. And the reason this starts counting from 1, and I'm going to tell you why, is because this was an exact copy of how MATLAB does it. Matplotlib was actually designed to be at least just equally capable and compatible with the plotting the way you do in MATLAB, just so a person coming from MATLAB can start plotting immediately in Matplotlib. And yeah, sadly, that means that something has to start counting from 1 because that's what MATLAB does. So 1 in the 2 by 3 means the very first one. At least the order by which you visit is still row first and then column. So let me actually just go ahead and plot it. So here's 2 by 3 subplots. You notice what I'm doing is I'm plotting x raised to different powers starting with 0. So if I raise it to 0, obviously it's going to be just 1. So it should be a flat line. Then I get a line. I get a quadratic function, so on and so forth. This is what I get. Right? So this is position 1, 2, 3, 4, 5, 6. That's how you specify, and that's what these are specifying. 2 by 3, position 6 is plotting x by x raised to the 5th power. Okay? Now you notice it's kind of all clumped up, right? Because you put a lot of subplots, the labels are overlapping with each other. It doesn't look that nice. This is where you can call PLT's tight layout function. What it does is that now it takes the subplots and kind of readjusts the spacing just to make sure that none of the labels overlap each other. So if you have a next cell, which I just added the tight layout, if you run it, it now positions nicely so nothing is overlapping with each other. Okay. Oftentimes this is all it takes. Sometimes you can really be nitty-gritty about exactly where you'd want the subplots to be placed. In that case, you manually specify. And sometimes that's what it takes to get exactly the plot you want. Okay, so now we visited the basic way of using matplotlib. I do want to step into a bit more of a very matplotlib specific way of using it. So as I mentioned already, matplotlib was designed to be very compatible with MATLAB's way of plotting. And this idea of just being able to do PLT plot, PLT subplot is exactly how MATLAB would plot it. But internally, matplotlib actually organizes things much more object-oriented fashion with concepts like figures, axes that are within each other. So let me just visit that. And this actually gives you a bit more harness of the power of the matplotlib once you understand it and learn how to use it. So first of all, every time you create a plot, say in the new cell you just say PLT plot, the very first thing that's implicitly done is creation of a figure object. A figure object you can just think is a container for everything you're about to plot. It's just a figure. So you can actually create an empty figure by using PLT figure. This returns, it's like an object instantiation where figure is sort of like a class. This is a function that returns an instance of figure. Anyway, it's creating a figure object and returns it to you. But in itself doesn't do anything because this is a completely empty figure. There's nothing to be shown here. So the thing becomes more interesting once you start adding stuff into this. And usually the next thing you add is an axis object. So while figure represents the whole figure, meaning not just the thing you plot but all the margins, background, and everything, axis represents that particular area of axis where you can plot stuff. So axis is a container for actual data points. So there's one way to create would be actually create a figure, create an axis with the axis function, and then add the axis into the figure. Once you do all of this, you basically get an empty axis inside a figure. So this is an axis, and implicitly the container that contains the axis is your figure. That's how they internally represents this data. Okay, you can say, oh, isn't that kind of inconvenient? Now I have to take like 3 lines just to create an empty axis. Right, so there's a bit better way. You can actually say plot subplot. So this is a function that by default returns one axis in a new figure and goes ahead and returns you figure and axis object. And it returns as a tuple, so you're doing this expansion to get the fig and axis. So if you do that, again, it's the same idea. It created a figure, it created an axis, place it in the figure, and just return it to you. So you're seeing an empty axis here. Finally, when you have an axis to axis object, you actually can use that to do plotting inside. So instead of using PLT plot, which implicitly creates a figure if it doesn't exist, and implicitly creates an axis if it didn't exist, and then starts plotting into them, you're here being much more specific that you want to plot into that axis object by using ax and methods on it. So here I create a fig and x with the subplots. And then now I have a data point for x, and I'm using axis plot method to plot a line inside of that axis. Okay. Ultimately speaking, you just achieve what you would achieve with plt.plot x squared. Okay, so at this point you might be wondering, like, why are we taking so many more steps? Like, I could have just done the plt.plot and that would have been it. And now you take so many more steps and it looks like you just achieved just as much. True, if this is the only thing you do with it, then there's really no reason to go with this method. But the real power comes by the fact that now you have explicit handles onto figures and axes. And this means you can actually create multiple figures side by side, and you can go back and forth about where you're plotting what. So here I'm actually plotting 2 figures and 2 axes. I mean pairs of it. Basically, axis is into the figure. X1 is in the axis of a figure 1, and x2 is in the figure 2. I create one x variable to store a number between 0 and 1, 30 data points. And first I plot it in the first axis, that'll be in the first figure therefore, a quadratic function. And the second axis I plot the cubic function. But now I go back and say, oh, I forgot to plot a line on the first axis, so I can just go back to x1.plot to be able to plot it in the first figure. This ability to go back and forth or just go to whichever axis and then start plotting is something you wouldn't quite get if you're stuck with PLT plot method, because that one always just plots in the most recent figure, most recent axis. So if I run this, you get two figures side by side, and basically went quadratic first, and then did the cubic, and then went back and draw the line. Okay?
So it treats it as a new plot rather than replacing the values in the first plot.
That is correct. That is correct. All right, but the real strength, and I obviously didn't know how to spell this, strength, comes when you're actually doing subplots. So earlier we did the subplot with the PLT subplot, something like 2 by 3, 1, and I already complained about the fact that starts counting with 1. And if you want to have multiple panels, you have to do that line many times, just changing something subtly. Of course, we're programmers now. We actually want to do this programmatically. We want to be as lazy as possible. That's actually one theme of programming, is don't repeat yourself, right? The computer can repeat all you want. You don't want to repeat yourself because you want to be a bit lazy about this. That's a virtue for a programmer, right? So what I want is now I'm creating a subplot that's 3 by 3 subplot. So if I don't pass anything in, by default it just creates one axis, and that's what I get returned. This time I'm passing 3 by 3, 3, 3 to indicate I want 3 by 3 subplots, 9 subplots in total. What that does is gives me one figure, because everything is going to be contained within one figure object, but axis object, which is now a NumPy array of many axis object. So you can verify that by running it. So it already goes ahead, creates the 3 by 3 subplots. And if you look at axis, this is actually a NumPy array of 9 axis object organized in 3 by 3 fashion. You can verify by the fact that it has a shape of 3 by 3. And one thing that's nice now is that this is a NumPy array of something, so you can flatten it by Ravel and just visit one by one and do plotting inside. So here what I'm doing is I'm going to take x, which is from -1 to 1. I'm going to visit every one of the x, and on each of them plot x by x, so a straight line. So I can programmatically easily get 9 plots filled with the same content. Now, of course, 9 subpanels filled with exactly the same content is exceedingly boring. What you want to do is something even fancier. You want to plot something different based on the position. So do you guys remember enumerate? If I have something that's iterable, if I wrap it with enumerate, it returns the content of iterable paired with the index. So here, by saying enumerate over axis Ravel, I get the ax object that I'm visiting, but also position within. And now what I'm going to do is I'm going to use the I to control what's the figure I'm generating. This is going to start counting from 0, going all the way up to 8. So I'm saying like, oh, why don't I just plot x raised to that index? And that's what I do. And now you just quickly and easily got x to 0, which is just a flat line, linear, quadratic, cubic, so on and so forth. And I also notice that I also control the title, giving something that is according to the position. One difference, however, you hopefully notice is that it's not ax.title, it's ax.setTitle. This is one thing that will be a bit annoying difference between if you were to just use PLT version of things versus ax version of things. PLT commands are completely equivalent to MATLAB, so they just pretty much took what MATLAB had it. When it comes to more of object-based plotting, like the way they do it here, which is more inherent to inherent to Matplotlib, they really took the method name to be something they felt was more appropriate. Here you're setting the title, so the method is setTitle. Okay, so there's going to be a bit of this difference. Usually it's just a difference between xlabel versus setxlabel, xtix versus segxtix. So it's not hard to figure out, but there will be some difference. Now notice again, this is pretty jam-packed up with each other with a lot of overlap. with the PLT, we would have used plt.typeLayout. That's actually really a command on the figure. It's a way to tell figure that, hey, you have to space things apart. We have a figure object, fig. So we actually tell the fig that we want the type layout on it. So repeat this with fig.typeLayout, and now it spaces apart, and you get a nice and clean tree-by-tree plot showing different functions. And a couple nice things. So if this hasn't really been convincing yet, another nice thing is that with this object level control, you can really start to control individual part of your figure and make property changes. So for example, I want the figure to be bigger. Well, there's a property of a figure. So you can actually specify the figure size upon creation of the figure, which happens at subplots. Now you can actually even do it after the fact. Given the fact you have a fig object, you can actually go fig set size in inches to change the size later on. But here I'm going ahead and specify figure size, and this is given in inches. And it is actually inches, meaning that if you were to take this figure and save it into, say, PNG or PDF, it does have this dimension specified. So that's really nice because when it comes to actually putting figures in journal, there are space specification, like size specification. You need to know whether it's supposed to be all the way to 3.5 inches, 7.2 inches. These things matter. So being able to actually specify in inches can save a lot of time later on. So you do this, and it creates a bigger plot. Now notice that it's not the most crisp, clear plot. Like it has a bit of blurring in it because it's not using a lot of dots per inches. It's not really well pixelated. So dots per inch is a way to represent how many pixels goes into an inch. It controls basically how nicely looking your plot is. And you can change that by actually passing in DPI keyword argument. So default is about 100, which is pretty low quality by many standards. 200 is considered okay. 300 is usually considered to be the de facto high resolution. So here I'm saying DPI.
I have a lunch delivery for this room.
So the DPI to 200 to be okay quality. And hopefully you see the fact this looks cleaner and crisper than the previous one. At least numbers tend to come better. And you can even get better if you actually go for highest, which would be something like 300. You usually wouldn't go too much higher than that. Okay, and just to wrap up things, and here I'm just going to be very quickly show you other kinds of plots. So far we've only been using plot to do line plots, and obviously that's not the only kind of plots you ever want to do. You probably want to do bar plots, you want to do scatter plots. Don't worry, Matplotlib has it. Right? So bar plots, you actually use the plot.bar. So here I'm going back to the PLT based ones, but obviously you can always still use the axis and object based one I just demonstrated. Here I'm just doing it for the sake of ease in terms of PLT. So I can make a bar plot specifying X locations and the value that gets us a bar. So here I'm actually randomly drawing 12 samples and just plotting the value as a bar plot. So if I run this multiple times, it will be different every time. Another one is scatter plot, obviously. So scatter plot, instead of connecting everything with line, treating as a sequence, it just draws this as points and put it on there. So here I'm just drawing some independent samples from two normal distributions. So if I do it, it should just be a cloud of points. And this again, if you run it every time, you get different sample every time. One nice feature though is that scatterplot takes this extra argument, keyword argument called C, standing for color, and they actually color code points according to the value you specify. So here I'm actually taking X and Y, so there are 100 points corresponding to each other, and I'm taking the absolute difference in their values. And I just pass it in as a C to see what happens. And notice that I'm putting this color bar because the color bar would be important to indicate what is the color corresponding to. So here it's color coding each point according to the difference in the value between the 2 points. So dark means they're very similar, yellower means they're very far apart. And here's yet another one. This we're actually going to visit next week when we visit the linear regression topic. But here basically I have a line I plotted first. So here I compute the ax plus b, where a is 5 and b is 10. So this is 5x plus 10 line. So that's my ground truth. And from here, I also sample a couple data points. So what I do is I take sample x values, which is just equally spaced samples of x values, compute the actual y, but I'm also adding some random noise. I take some random variable from normal distribution and scale it a bit so it's not ridiculously big noise, but just add them. And net effect is that these samples are noisy samples of underlying line. So this would be something like what a linear regression would try to do. So linear regression will actually go from the sample points to try to figure out what the underlying line was under some model of the noise. So here you can actually try a different one. It always looks a bit different. And if you change the scaling here, so here's the standard deviation is actually 0.5. That's what this will do. If I make it 5, so 10 times as big, well, you can really not tell anymore. There's a line here, right? So remember, in the reality, you only see the data points. Here I'm basically telling you that the line is the actual model, but what you get to see as an experimentalist or scientist is just the data points, and your job is to try to guess what the underlying line was. And here, you're probably not going to be having too much of a good time. A lot of people will be convinced there's not a line here. Now, of course, if you make the noise small enough, then you can really start to see the line, right? So this is the topic of linear regression we're going to visit next week. And last but not least, this is also something we'll take one session next week to really kind of play around with, and it's pretty fun, is the topic of images. So this could be multi-photon image or just like image you take out there, right? So interesting enough, in NumPy, image is nothing but a NumPy array. So not in Matplotlib or in just in scientific computation in Python, image is nothing but a NumPy array with enough dimensions and sizes. So here I'm creating 128 by 128 random matrix, and well, you can actually treat that as an image. Nothing wrong with it. It doesn't have red, green, and blue, meaning that this is going to be treated as a monotonic color scale image. But whatever, you just plot it and you see noise. This is what you see potentially on TV screen back in like, I don't know, 10 years ago. Nowadays, I don't think you get as many of this. Okay, fine, this is somewhat colored. You can actually change the color map because this is just taking some value and mapping it to color to indicate the value. You can change this mapping. It's called color map. And you can change it by specifying CMap when you use this IMShow to plot the image. So if you do gray, well, now it shows in grayscale. There's another one called jet, which probably no one should ever use, but I'm showing just for the sake of it. There's a jet color scheme. And if you ever want to see, okay, what is this actually color corresponding to, you can plot the color by next to it. And you can see that jet is showing value between -4 to 4, mapping into some color. The reason I'm saying this is because jet has been considered to be one of the worst color scheme you can ever use and it's been established for quite a few decades now, so please don't use jet. I'm just showing it as a bad example. I'm not trying to promote that you should be using jet. Okay, and then last but not least, you can get more interesting images. We've been seeing what people will call white noise image. If that terminology makes sense to you, what you just plotted is a white noise image. Let's get something more. So here I'm just actually using a SciPy package, which I'm not really going to go into in this session. It's just some scientific Python computation packages. And one of the things it has is this face function in it. So I'm specifically importing this face function. And the reason I'm doing that is that if you call it, it gives you an image of a face. Okay, well, let's just see it. Well, it's a face of raccoon. Right? It used to be some other image, but they decided to replace it with raccoon. And here again, it plotted with some default color scheme. I can change it by CMap for gray. Now it's more in grayscale image. And if I say cool, it shows in the cool color scheme. And it's not cool in this, well, it's cool. Sure, it's cool. All right, so I know that was quite a bit of rush, but that's what I wanted to talk about with NumPy and Matplotlib, and I'm glad we made it through. So at this point in the last 5 minutes, which I have to allocate at least 3 minutes arranging the room, I'm going to very quickly talk about homework assignment. What's going to happen is that I'll be posting a link on on the Slack channel. And let me see if I can quickly go there. So the way I'm going to have homework assignments submitted from now on is through Git. Basically, you'll be invited to a Git repository specific to you, and it will contain homework assignment description, okay? And you're supposed to accept my invitation, first of all. Yeah, accept the invitation, be part of that repository, and then clone it, follow the instructions, put your assignment in it, add, commit, and push it to the repository. And that act itself is submission of your homework. Nice thing is that means you can do submission as many times as you like. If you made a commit and you're not quite happy about it, go ahead, make yet another commit, push it. Basically, at a certain point, I'm going to say, okay, This is done. You cannot keep on changing it. I'm just going to look at what you have. Given this is not a graded course, I'm not going to be that strict about it. I'm just going to basically see how long you've been inactive for, and when I just get a chance to, I'll just look at the code and give you some comments. I haven't quite exactly decided on exactly how I'm going to come back with the comments. Most likely, I'll use something like a pull request or issue. You'll figure out. Basically, today you will receive an invitation for a sample homework whose whole purpose is for you to try the Git and GitHub and make sure the whole scheme works. It's a good exercise to make sure you have learned Git well enough as well. So we get an invite. It will be a repository. There will be a document describing what you're supposed to do. You have to clone it, add something, and push it. I want you to do this exercise. I already provided a PDF last night for you to be able to follow through some of the commands we covered in the last session. All right, that's it. So let's put the room back. Yes?
If you don't recommend JET, what color map would you
Hmm?
recommend? If you don't recommend JET, what color map?
What color map I recommend? That's a very good question. So there are many. I can actually send personal ones, not personal ones, but I can send you references. There is another package that almost everyone uses with Matplotlib that gives you far richer set of color maps, and with the feature being that it has features like being correctly linearly scaled, such that every step in the value corresponds to linear step in what we perceive to be same value. I can send you. It's a long topic. There's many papers associated with this, but I can just basically send a page where it lists good color maps. All right, that's it. So yeah, let's put the